50 minutes of me prattling on, then you can go to the pub. I will start by saying I'm aware that there are quite a lot of non-native English speakers here, and I'm from a part of England known as the North. So I will try to speak slowly and clearly, but if you have trouble understanding and I start sounding too much like Ned Stark, please shout out. I'm quite happy to repeat things. So quick show of hands. Who here has worked on some kind of event log stroke messaging system, Kafka, MQ, something like that? Okay, quite a lot of people. So, and who here has worked on any kind of system that in some way interacts with a backend database? I mean everyone, right? So the thing about databases is that they are inherently a state-based view of your data. You have tables, you have relations between those tables, and you don't have to think too hard about getting the state out. Select star from table where ID equals whatever, and you've got whatever piece of the state that you need. But an event log is time-based. And if you kind of, like me, you've grown up on database systems, you kind of take access to the state for granted. It's there, it's really easy to get hold of. In a time-based view of data, it's a bit harder. You have to do work. You can't just magically get the state. You have to do work to infer that state. And if you don't address that, you could get in a lot of pain. So some fundamentals about state in the event log. So any system has state. The world has state, and it has events occurring going through it. And whatever the state is, that's going to kind of dictate what events are going to happen. And those events happen, and they change the state. But they're not interchangeable. A persistent event log is not a substitute for your state store, and vice versa. You can have a state store, and if you log those changes over time, you can infer the event log. And you can take the event log, and if you read it, you can work out the state. But you cannot look at the event log and immediately know the state. Nor can you look at the state and know what the log of events is that caused that state. So they're associated, but they're not interchangeable. So a little bit more about me and where I come from, so you can understand the use case that we're going to be talking about. So I work for William Hill. We're one of the oldest and most well-established companies in the gaming industry. And I work in the trading department. We deal with sports betting, and we basically trade what happens in a sports event. So the way odds are created these days has evolved quite significantly. We basically take all kinds of input, some of it about what's going on in the event, some of it about what's going on in the market, and we create our prices from that. So it's a kind of trading model. We deal with a lot of sporting events, about 200,000 a year. And we publish the odds for those events, and we also result the markets once the events are concluded. And we cater for both longer living pre-match markets, so where you want to bet on the outcome before the game started, but we also do in-play markets, which are very big these days. And we've been building applications with messaging technology for quite a long time, because it very much suits our event-based use cases. So what do we do in the simplest terms? So we take a bunch of third-party feeds. So we take some information about fixtures. So maybe Premier League fixtures, Man City against Liverpool, NFL fixtures, Cowboys against the Giants. We take incidents, so things that are going on in the game, goals, throw-ins, touchdowns, whatever it is, and opinion. So what's going on in the marketplace? What odds are other bookmakers offering? Because in this day and age, you can't leave yourself open to arbitrage. You have to be very careful about that. We put all that data into these sort of mathematical models, and they spit out all these markets. So all these different markets with a whole bunch of selections and a whole bunch of prices. And some of that information goes to the scoreboard, some of it goes to the website so people can place bets, some of it goes to back office so traders can keep an eye on things. So in terms of how that translates to what we build, so we have a bunch of feed handler apps that ingest those deltas from third-party feeds. They generally get transformed into some kind of internal type of view, and that gets put on Kafka topics. So some of the information is long-living, so fixtures can live for a long time, typically days, but sometimes weeks or months. So World Cup draw, they draw the first round, that's done in December. Those games aren't going to get played till June. So those games exist for a long time, but fixtures typically live for days. And then there's opinion data. Some of that's long-lived, so anything pre-match is going to be long-lived. Anything in play is going to be short-lived. And then there are incidents, and they're typically minutes or hours, because that's the duration of the event. That gets munged into a whole bunch of microservices, and we basically push it all into this stateless mathematical model. So the model itself is stateless, which means we need to pull full state into it. And what we get out is markets and prices, and we then distribute those. So in a nutshell, that's what we do. So if we think about features of the system, we have a combination of long-living data and short-living data. We have a combination of stateless and stateful services. Those pricing models, as I say, they are stateless in themselves, but they require the full state of the event in order to do the processing. And the input data is just stateless deltas. So a throw-in's happened, a corner's happened. And we have microservices wired together with Kafka. And Kafka is used as both a data transport mechanism and a data storage mechanism. And you need to be aware of that from the start, that you're mixing use cases there. If you view it as a stateless pipeline of delta messages, pretty straightforward. It's just stuff happening. It's a bunch of idempotent messages, dead easy. But once you start to introduce state management, it starts to get a bit more complex. So the first thing we tried to do is build it out where we said the state's in the event log. And you end up with sort of something like this, where at the top there, you have a publishing application that publishes delta messages to a topic. And then you have downstream applications. They have no persisted state in themselves. So when they start up, they read either from the beginning of the topic or maybe from an earlier offset, and they build any required state. And it sort of sounds great in theory. Oh, start up, build state, don't need a database, this is brilliant. But when you start to think about startup time and durability, you start getting headaches and you start getting problems. And also, if you're doing this all over the place, so you've got topics between all your messages, your state starts to become distributed. Like, where is your state if you have all these topics? So in terms of game state and game events, so we have to process events. So if there's in the case of football, if there's a goal or a substitution, and those game events affect the game state and therefore the prices. So if Manchester City are playing Liverpool and Sergio Aguero scores for Manchester City, the odds of Manchester City winning the game are going to shorten, and the odds of Liverpool winning the game are going to lengthen. So all of these events can affect the prices. But the problem is we weren't inherently storing the game state. It was kind of in the Kafka topic somewhere, which is fine if you're doing just sort of dumb pass-through stuff. But once you have kind of certain edge cases, and particularly once you start thinking about performance and how fast your services need to start up in particular, you start to have problems. And you also have this problem of if you have multiple topics, where's your state? Which one contains the state? If you're passing more or less the same information through dozens of topics, wiring up hundreds of microservices, where's your state? And that leads to the sound of inevitability. I used to think putting that on stuff made me look cool, but then I realized it's 20 years old. It just makes me look old now. So if you do not have a golden copy of state, if you do not have that single source of the truth, global state mutation is going to become an inevitability. So I'm not going to sort of go into why global state mutation is bad. I'm going to sort of take it as read. Global state mutation is bad, okay? So it's like kind of eventual consistency, but where you're never consistent. So you start to realize, actually, that golden copy, that's really important. And if I've got all these topics, I don't really have it anymore. So, and this is where you have data storage versus data transportation. As I said earlier, we're using Kafka for storage and transportation. And it's fine, you can use it for both, but you need to be really careful when you mix those use cases. So if you're using it for transportation, that implies, and some of you here have used Kafka probably doing the same thing, that implies you've probably got lots of microservices and you've wired them up with Kafka. And there's plenty of people out there doing that. And that's fine. And if you're using Kafka for data storage for durability, that is to say, you're using Kafka between microservices so that if your service goes down, it can come back up and it's not going to miss any messages. Because if you're using HTTP, your service is down, and you've got no way of knowing if you've missed requests, and you don't know if your client is going to resend those requests. But with Kafka, pop back up, messages are still there. So if you're using storage for that use case, that's absolutely fine. But if you're using it to store your state, and you've got lots of topics, where's your state? Where's your golden copy? So this leads to the Abramson Law of event log systems. I've always fancied having a law. A lot of people have been talking about Conway's law. I'm not sure my law's catchy enough, but I'm going to attempt to blag a law. So in a stateful system, it is essential to have a golden copy of the truth of your state, crucially, available in real time. If it's kind of munged away in your Kafka topic somewhere, and you've got to read 3 or 4 topics and put it all together, that's kind of useless. You've got to have it available in real time. And that's a quote from me right now. So today is the birth of Abramson Law. So again, going back to our use case. So we sort of had a lot of situations where in order to process event X, we need to know Y about the event. So if the home team have scored a goal, in order to update the score, we need to know what the score already was. And some parts of the system could work fine on deltas, but others required full state or partial state. So we started thinking, well, maybe we could cache some stuff, or maybe we could sort of add metadata to messages, which was kind of okay, but it quite quickly got out of hand. And this led us to the sort of classic Kafka AntiPattern. And if you've sort of talked about Kafka, or you've had an introduction to Kafka, or someone's been explaining Kafka to you, they're probably giving you a quote, something like this. To get the full state, you just read the event log from the beginning. It's easy, you don't need a state store, and you're away. And that's actually a very famous quote, and that's a very famous quote by people who don't understand Kafka. If you're reading millions or even billions of messages, it's going to take time. Even if they're small, even though Kafka is super fast, it's going to take time. And you cannot just approximate that to real time, because it may well not be. And your event log is not a replacement for your state store. And if you think that it is, you're going to get into a world of pain. So, attempt 2, we had state where necessary. So sort of either in metadata or cached. And again, in those cases of, in order to process event X, we need to know Y about the event. So we started to cache data for that. So for example, corners. So corner markets are generally based on the number of corners, so you can bet on the home team is going to have at least 3 corners in the first half. So if a message comes through from a feed saying that the home team's got a corner, you kind of need to know how many corners they've had, because you need to result that market. A key thing in sports betting is punters want to be paid out as quickly as possible. You can't wait till the end of the event and then result all the in-play markets. If a punter's bet on 3 corners and there's a 3rd corner in the 18th minute, they're going to want their money by the 25th minute at the latest. And if you don't give them that, you're going to lose your customer. So you can't just sort of wait till the end. You've got to be able to result things in real time, which means you've got to know all this data in real time. So where do you keep those running totals? Well, you can cache it, and that kind of works. Well, it works until your service restarts. And then sort of suddenly you realize that you've not solved that problem at all, you've just masked it. Because actually, if you've got caching without an underlying layer of persistence, you gain nothing in terms of failure recovery. Because when your service comes back up, it's going to have to repopulate the cache, read from the beginning, and actually all you've done is masked your problem. So we started looking at metadata. And we started adding metadata to messages that required some of the state. And I'm going to go out on a limb and say most people have experienced something like this, where some architect hasn't thought of something, and they go, oh, just add a bit of metadata. And then, like, 3 months later, you've got a message header that's about 3 meg in size. I think a lot of us have experienced something like that. If you've got 1 or 2 fields, fine, But you will end up with a lot of data in this sort of use case. And also, metadata is really hard to type. So you end up with a lot of this sort of guff. You are doing your developers no favors whatsoever if they have to deal with object structures like that. Because they're going to come in and think, oh, what on earth is that? And even if they figure out what it is, they'll come back to it 2 months later and think, what's this again? This is like, objects exist so you don't have to have things like this. So metadata is quite hard to type, and you'll end up with really nasty stuff like that. And also, messages became very large and very unwieldy, and that had an overhead in itself. So the benefits of caching and metadata proved to be limited. And they solved problems, but they introduced others. Or in the case of caching, they really just masked it. Because with the non-persistent cache, you're going to have the same problem when it fails anyway. And if you put a lot of metadata into your messages, rereading from the start becomes a big job because you're reading big messages. And some of our services were taking up to 40 minutes to start. And no one's going to be all right with that. So we then went to the next attempt, which was full state messages, which kind of sounds a bit crazy, but bear with me. So it's a bit of a chicken and egg. Because if you don't have an explicit state store, your state if it's not in your services, it's got to be in your messages. And there's the chicken and there's the egg. So why pass full state? Because it does sound a bit crazy. Well, actually, there's some benefits. You think about all that failure recovery. Full state fixes that. If you've got a full state message, you don't need to cache anything. You don't need to reread anything. Everything can be stateless. Because all you need to process something is the next message. You don't need to read up to the offset. You don't need to cache anything. You don't need to look anything up. Dead easy. So for us, the state was maintained in a sort of at the top of the stack in the feed handlers. And then the deltas were converted into full state messages and passed down the stack. And this was pretty powerful. Because it's very durable and very performant. Because messages can be processed asynchronously. So you can read your latest offset over here. And even if that takes a little while to process, or if it's particularly busy, so Saturday afternoon, there's 250 football matches going on around Europe, and you're getting lots of messages. So when you're done, you commit the offset, you can drop those messages, just go straight to the latest offset. So as long as your service is still sort of processing in a fairly timely manner, you're never really going to get behind. And that's actually a really powerful durability and performance guarantee. So we sort of ended up with something like this, where we had the deltas going into the feed handler apps. We were kind of holding it state there and then passing full state and going to these downstream apps. The thing is, it's not really an event log now. If you're passing absolutely everything, it's not really an event log. So while we had those powerful durability guarantees, we did experience some drawbacks. So one is messages can get really big. And anyone who's worked with Kafka will know that 9 meg for a message is crazy. So some of our, particularly our Premier League games where we have lots and lots of markets, lots of in-play markets, lots and lots of things happening, they could get very, very big. And 9 meg is crazy big, because the Kafka system I worked on before this, the messages were 14 bytes. So it's quite a step up. And also, it makes your services kind of inefficient. if you've got a service that's only interested in 2 or 3 pieces of data and it's having to deserialize a 9 meg message, look at a couple of pieces of data, do something with it, and then reserialize it and put it on the next topic, that's a massive overhead. You're making your service do an incredible amount of work. And also, it created a problem for developers because understanding the full message required a lot of knowledge. I was in the domain-driven design session yesterday. I don't know if anybody else was in that with Carola Lilienthal. If you weren't in it, really good session. Check it out online afterwards. And so one of the key takeaways of her session was that if you create a domain model that's got everything in it, and then you make everything depend on it, you're going to be in a world of pain. And that's kind of where you get to with a full state message, because it's your entire domain model in every single message, and everything's dependent on it. And Carola, if you're watching, that's a world of pain. I can vouch for that firsthand. And it made it very difficult for the developers. Very few people understood the full message end to end. And it's inefficient because it's essentially an event log where every entry is in itself an event log, because every message is everything that's happened. So, it's I know we're kind of in a flat data world these days, but that's taking it to crazy degrees. But that said, I wouldn't say passing full state is an absolute no-no. I don't think it's a complete red line. There may be some edge cases where it might be appropriate. If those durability guarantees, they're really powerful. So if you need that durability, and particularly if your state is sufficiently small, and I think that's probably the key one, your state would have to be sufficiently small, you could think about doing that. But it's an edge case, and in hindsight, it's probably not appropriate for this use case. So we also had a bit of a go at Kafka Streams. We didn't get very far with it, which is why it's an abandoned attempt. Kafka Streams, they're pretty cool, and they offered a lot of solutions to our problems. So you have that fast data access. So anyone who's used Streams was probably familiar with KSQL, where you can sort of effectively query the stream in real time, which is exactly what you need. It gives you exactly once processing semantics out the box. So for us, that's really important. If it's Man City versus Liverpool, Mohamed Salah scores a goal, we want it to say 1-0, not 0-0, not 2-0. It needs to say 1-0. So exactly once is really important for us. You get the continually updated data set, and you get some really powerful data processing operations. So K-Streams gave us the opportunity to solve a lot of these problems. But we had some issues. So we were playing around with Kafka Streams a couple of years ago. So this was 2017. And it was pretty mature when we were playing with it. And again, the problems we had were around failure recovery. So particularly we found that if a rebalance happened, that the stream would just get into this kind of tiz that it just couldn't get out of. And what we ended up having to do was hard killing the app. And something's a bit wrong if you're typing system.exit into your code. It doesn't feel quite right. And although we did that, we were finding that we'd then have to restart the app, we'd have to rebuild the data set, and we couldn't support that inside the SLAs. So we sort of had to abandon it. It's definitely worth saying, though, it's a lot more robust now, and we would like to go back to it at some point and have another play with it. So please don't be put off Kafka Streams by what I'm saying. It was very immature at the time. So I think if you did it now, it's probably a lot more robust. So then, attempt number 4, the state store. So yes, we brought databases back because basically you've got three storage options. It's either you're either going to cache it in your service somehow, you're going to pull it out your topic either by reading from the beginning or having full state messages, or you have a state store. And we'd had problems trying to keep it reliably in the service. We'd have problems getting it out of the topic in a timely fashion, or in a way that didn't break everything because the message was too big. So we just thought, actually, do you know what? Maybe we should try going back to state stores. So the return of the state stores. So when we reintroduced it, it brought all those benefits that you take for granted. You spend your career working with databases, and you take for granted what they give you. They gave us that golden copy of the truth. It was fully persistent, and it's readily available. And you work without a state store for a while. You bring it back in, and you think, geez, these are really good. Databases rock. But there's a reason people have been using them for half a century. They do some really good jobs. And suddenly you're like, yeah, doing all that with Kafka and no state store, really hard. I mean, don't get me wrong, Kafka's great, but it's not something that you can solve every problem in the world with. Using it with a state store, this is brilliant. So it immediately solved many of those performance and persistence problems that we'd been experiencing. And it also allowed us to rationalize and simplify our estate. So in a number of places previously, we had sort of something like this, where you have a publishing app, you put it on a primary topic, you have an intermediate app, it does some kind of filtering, puts it on an intermediate topic, and you have your consuming app. We were able to change this in quite a lot of places, where the publishing app writes to a primary topic, and the consuming app has a state store. And it can write to that state store, it can read from that state store, and that's how it gets its durability guarantee. So we were able to rationalize and simplify our state. So, as I've said, in many places, two services joined by a Kafka topic could be changed into one service with a Cassandra table. And in a couple of places, I think we replaced 4 services with a single service, which was brilliant. And a lot of those startup problems just went away, because you start your service, you read from the database table, and then you just start reading from either the latest or the last committed offset, and off you go. And while the database did introduce more latency, that's why we tried to get rid of it in the first place, to avoid the latency of a database. It did introduce a bit more latency, but given that we had less services and less Kafka hops, that kind of offset it. And when we introduced it, we found that when we were testing end-to-end, actually, it didn't really add much time. It didn't really change the time at all, to be honest. And also, querying the state was now something that could be done in real time. You only realize how valuable that is when it suddenly becomes really difficult to do. So, if you're going to use a state store in this kind of architecture, there's definitely some things you need to think carefully about. So, you probably heard this a lot. In a microservice architecture, each service should have its own store. There's a lot of dogma around that. It must have its own tables. Nothing else can talk to those tables. And if anything else talks to those tables, it's not a proper microservice. A lot of people get very upset about that kind of thing. And that's fine in a kind of classic data service world, but it's a bit more complex in a data pipeline. So it's fine if you've got something like this. So if you've got, say, customer data, you can have a service for email addresses, services, postal addresses, so on and so forth. It's pretty straightforward. If you have something like this, it's a bit harder. If some of the services down here need some of the data that's up there, if you don't allow them some kind of read access, you've got all the same problems again, because you've somehow got to get the data down through Kafka, and that can be a bit of a pain. So we came up with a number of options. So there's the closed state store, which is basically the classic microservice thing. This is my microservice, this is its tables, and no one else shall know about it. But we also found that it was quite good to have what we called an open state store. So where you have a service that has a table or set of tables, and it is the owner and manager of those tables, nothing else can write to them, but we would allow other services to read to them. And I'm sure there's microservice ideologues who would go, yeah, but you should put in a REST interface so that you're calling it via a service and not accessing it directly. We didn't do that, partly for reasons of performance, but mainly for reasons of couldn't be bothered. There are some exceptions. So there are a couple of places where we'd have a sort of subsystem store, where a number of different services would be able to write to the same store. And that was quite often when we had information coming from several different sources that needed to be amalgamated. So we would have something like this. So a good example is goal scorer markets, where you bet on Man City to beat Liverpool and Sergio Aguero to score. So for that, you need information about the event, and the instance, but you also need information about lineups, which comes from a different source. And in order to construct those markets, you have to sort of amalgamate that data. And if you wanted to be really anal and have the microservice thing, you could do that, but it'd be really difficult. And actually centralizing data, it's another job that a database does really, really well. So we did that. And then there was the thing that we never attempted. That's change data capture. And I'm sure we've all worked on projects where we get to the end of it, and then we find out about something or we hear something and we go, yeah, it would have been really easy if we'd done that, wouldn't it? And for us, that was change data capture. So for those, I'm sure some of you have heard of change data capture, but for those of you who haven't, creating state from an event log is problematic. You've got to read it all. But creating an event log from state changes over time is actually pretty easy. And it's a job your database does for you. It's called the log file. You can just publish changes from the log file. And change data capture does exactly that. It just publishes changes to the state in real time. And it kind of looks something like this. So you have your database, which is kind of your golden copy, and you build the state in the database as you would. Services come in, interact with that data, and it holds the state. And then the state is available to anyone downstream who needs it because you just trigger these changes. So in hindsight, yeah, this would have been the best approach. And we could have had feed handlers basically sending those deltas straight into databases to update state. And then CDC would just create a single synchronous event and off it goes. And anybody who wants to act on that can. They just subscribe. I'm interested in that event. I'm going to trigger something. So for us, it would have probably looked something like this. So where we have changes from multiple feeds coming into the database, and CDC publish it via the changelog with a data connector. So there's loads of Kafka connectors that connect to pretty much any data store that will publish these changes for you. And it acts as a triggering mechanism for pricing. And the full state is obtained by going back to the database. So the really great thing about this is you no longer have to push all the garbage down through here. This becomes a really lean triggering mechanism. So all you care about is, this event's happened, oh, do I need to reprice? And if you do, you don't have to carry all the garbage that you need to reprice. You just go back to the state store. You go, oh, you need to reprice this. Oh, great, I'll go and get the state. And all that service pipeline would have been way simpler. So in hindsight, that would have been what we'd done. So lastly, this isn't particularly pertinent to state, but I think it's quite an important thing to talk about. We did a lot of what I call hardware limitation-driven architecture. And I'm sure many people have experienced similar things with ops departments who don't want to spend money on hardware. So in order to save money, our Kafka nodes had 60 gig disks. I have more disk on this phone. And that meant that our entire cluster had less than a terabyte, which meant we had to be really aggressive with compaction and deletion. And that compounded our problems. Because obviously with our full state messages, with reading from the beginning, we didn't have a lot of disk to play with. And we were having to architect for the fact that we didn't have a lot of disk. And it created more anti-patterns. And we ended up with a lot of this kind of thing, where you'd have a primary topic there, and because of the disk limitations, our retention time on that primary topic was 4 hours. And that was kind of okay for in-play, but for pre-match that would last for days, weeks, or longer, we'd have to write apps that would basically filter certain messages off and put them onto intermediate topics with longer retention times. And the bigger disks would have been far more optimal and cost-effective. You think about how much commodity hardware costs compared to how much developer costs. And it also further dissipated state. So where we had state up there, we now had state down here as well. So that became a real problem. And we also had a problem that we had our own self-built internal cloud. I don't think anybody does that now, but sort of, you go back 7 or 8 years, it's probably filed under, seemed like a good idea at the time. We're now trying to move to AWS, but we still have this self-built internal cloud. And one of the limitations it had is there was no durability or transferability of disk storage. So on your cloud node, you could write to disk, but if your service then went down and came back on another node, that disk information was gone. Which was, I mean, if you think about it, that's kind of removing a fundamental axiom of what a computer is, the ability to store data. So we weren't able to do that. So if we wanted to write something to a file locally or something in order to make a cache persistent, we couldn't do that. And then we had what I call the failover Russian doll. So we had Kafka nodes, which are managed by Zookeeper, that was sitting on our cloud, that was sitting on VMware, that was sitting on the underlying hardware. And that is just too many components to try and manage durability and failover. Because the cloud was trying to manage failover of everything, and Zookeeper was trying to manage failover of Kafka. And quite often, when things went wrong, they'd conflict, and that could cause recovery problems, and it also made it really, really difficult to see where the problems had happened and why they'd happened. So problem diagnosis became really, really difficult. So there are some cultural lessons here. It's really, really important that your ops people and your hardware suppliers understand your requirement for lots of disk. Because if they've not worked on big data systems, if they've not come across Kafka or Hadoop or any of these other tools, they're probably going to go, how much disk? Are you mad? So you need to be aware of that. But the way to play it is you need to point out that more disk is significantly cheaper than the cost of coding around issues, especially given that Kafka is designed for failure. So you don't need expensive SANs or RAIDs or anything like that. Commodity hardware will do. And if you think about how much a team of, say, 7 developers costs for one day, you could buy petabytes of commodity disk with that. So it's an absolute no-brainer. So your ops people telling you that you've got to spend weeks and weeks and weeks coding around issues caused by not enough disk, you need to point out that the cost of your team until lunchtime would pay for those disks many times over. So you really need to get that cultural lesson across. And also, make your failover mechanisms simple and not overly layered. Because if you've got loads and loads of things trying to manage that failover, that might seem, super safe. Yeah, I've got this and this and this and this. You tend to find they conflict. And even if they don't conflict, you can't necessarily see the wood for the trees. You can't see what's falling over, what's trying to restart, and it becomes very difficult. So in summary, if you take one thing away from this talk, take this away. Your event log is not a substitute for your state store. Please don't think that it is. Kafka is brilliant. I love it to bits, but it is not a replacement for your database. It may contain the state, but it's not necessarily easily accessible. That said, there are still some use cases for building state from the start. So error replaying. So if you archive off messages into an OAT environment, if you then have a problem, you can run it up in the OAT environment, play the messages again, and see if you get the same problem. So that's a really powerful use case. Also reporting. No one wants to wait 5 minutes for a service to start, but they probably wait 5 minutes for a report. So there are some use cases where building the state from the start is kind of okay, but so that you can have state in real time, it's probably not one of them. You don't want to rely on that. Use caution when mixing Kafka for data transport and data storage. Just be careful of that, because you can quite easily find yourself, I'm doing both of these things, and I've not really actually sat down and thought about the implications of it. And following on from that, you must always maintain a golden copy of the truth. Where is your golden copy of the truth? Where is your single source of the truth? Because you will need one. And change data capture is a really powerful pattern, and there's some really good tools out there for it as well. So if you have requirements for availability and persistence, if you need to have fast access to your data and you need it in a persistent place, in certain circumstances, Kafka is going to struggle to do both. Kafka's brilliant, it's incredibly durable, it's very, very fast, but it cannot do all the jobs that your database does as well. You need to use it in conjunction with the database, not instead of. And Kafka's, it's that classic disruptive technology. It's really driven a train through messaging. You know, it's blown MQ out the water, really. And it's changed how we think about message-oriented and event log architecture completely. And good practice is definitely still emerging. I know for a lot of people it probably feels like Kafka's been around for ages, but good practice is still emerging. So don't be afraid to try different things, but crucially you need to be prepared to be wrong. So with all the microservices that we had, most of them probably had 2 or 3 different distinct versions before we got it right. And even then, you look back at some of the older stuff we've done now, it's like, well, I wouldn't do like that now. So you need to be prepared to be wrong. And ensure that everyone understands the implications, not just the developers. If you go out and decide that you're going to use Oracle and you buy an Oracle database, first thing you're going to do is hire an Oracle DBA. There isn't really such a thing as a Kafka administrator, and you tend to find that role sort of falls in the cracks between the developers and the ops guys. So it's really important that your ops guys are on board and that you cover that gap somehow, whether that's the developers, the ops guys, or probably a combination of both, or training someone up to sit in the gap. You need to make sure that everybody understands the implications. So some resources, we consulted with Confluent. They were really good, really useful. The Definitive Guide to Kafka, that's a pretty good book, recommend that. And there's some Confluent examples for Kafka. There's a reference architecture. I'm not sure how relevant that still is. I think that link's a few years old. It probably still works, but I'm not sure how relevant that reference architecture still is. But do check it out. Any questions?
Have you ever configured a Flink on your system?
Yes, but it's... Yeah, I kind of got a bit annoyed about that because, they're not really quite the same. Flink for Kafka Streams, yeah, but Flink is... There was someone came in and was like, oh, yeah, let's use Flink. And I was like, it's kind of quite different. It does some of the stream stuff, but it would mean quite major re-architecting. I think, Flink's a great tool. Not that I've used it too much, but it's not a case of, certainly what I've seen of it, it's not a case of you can just sub it in. I would say Flink's probably more similar to something like Spark than Kafka, but it's powerful. It's cool. It's something I would like to use more. So.
Yeah, just an observation there. You were talking about chain shaped capture. We've tried that, and that also brings about a load of problems in that if you've got multiple things before your event is finished, you'll be picked up too early.
Oh, okay. Yeah. Yes. Yeah, I guess it's one of those things when you start using it, I'm sure a few problems come out. But I think it's probably still better than trying to push your entire state through a massive pipeline. But yes, I can imagine that there are problems you need to be cognizant of. Any more questions? To the pub. Thank you.